Thank you very much. Can you hear me? I suppose
Yeah,
you can hear me, and the slides are also good, I suppose. Can you see my slides? That's the
yeah. This is the title.
okay, good. All right, thank you very much. First, Physicist, thank you very much for inviting me. It's a great pleasure to give a talk. Although some of you, it's not a good time, including me. It's 12:30 a.m., but still, I think I'm fine. And some of Israel people, it's probably dinner time, but I hope I can do some good job to give something. So this is a bit different from enumerative combinatorics, but there are some techniques from enumerative combinatorics, so I like to talk about a little bit about this. And if you are interested in algebraic geometry, sometimes what we are trying to do is called tight coloring. It's exactly sledge coloring. So I think that that's very connected to the many fields, including, of course, the graph theory. So I hope that you can get something. So this is a work based on this paper. It's already archived. So if you want to see more details, please go to the archive and you can see that. Moreover, there's a GitHub here that you can get to some implemental result and the codes over there. So to begin with, let me just give you some contents of my talk. The first thing I like to talk about is basically the focal theorem and the equivalent formula. And then I will talk about our main result and implementation. And then the third step, I'm essentially giving you a sketch of proof of the focal theorem and also our stuff. And if I have a time, I really want to talk a little about the main difficulties of a focal theorem because our stuff is more general than the focal theorem. So there are some difficulties over the focal theorem. And finally, I'd like to talk some open problems and some ongoing project. So the main topic of this talk is graph coloring. I suppose everybody knows that, but graph coloring is basically color vertices so that if the edges are here, then the two adjacent vertices must receive the different colors. And the main focus will be like the focal theorem, which is basically coloring the maps at the beginning. And that's equivalent to the coloring the planar graphs. So history of the focal theorem is quite interesting. Well, probably some of you already knows, but let me just repeat. So it was first noticed by the Kasuria, who actually creating a maps, and he and his brother already noticed that if you color the maps so that two adjacent regions receive different colors, you only need four colors. There were no exception that they realized. So then basically they thought that maybe four is enough. And then the Morgan probably formulated the problem for three. And then there's a letter from Morgan to Hamilton around 1852. The visibility is probably done by, it's more visible. This problem is more visible in 1878 by Cayley. Cayley submitted the problem to London Math Society. And then Kempe claimed that he had a proof. And in fact, so far, the focal problem was focal theorem for 10 years, but it turns out that he would point out an error, and what Kempe really proved is actually five color theorem. And then, so since then, it was open and finally proved by Apple and Hakem. And today, we also talk about a little bit of Robertson, Sanders, Seymour Thomas. They gave actually the shorter proof, better in a sense, many sense better proof. Actually, I'm talking about not the vertex coloring, but the edge coloring, because it's following all result by type. So type 1880s, indeed 1880s, he already noticed that focal theorem is really equivalent to that every richest cubic planar graph is 3H colorable. 3H coloring cubic graph is sometimes called tight coloring. Bridgeless means that you can't have one edge cut like this. So that's called bridge. Three edge coloring, it's basically coloring edges, not vertices. But if the edges share vertices, they have to receive the different colors. And the point is that because we are talking about cubic graph, which means that every vertex has a degree 3, so you really need 3 colors, 3 edge coloring. And the question is when you really color with only 3 edge coloring. So that's more interesting part. And Tite basically said that focal theorem is equivalent to show that every bridgeless cubic planar graph is 3 edge colorable. Now, 3 edge coloring cubic graph, type coloring, if you want to call, that actually got a lot of attention even from the 19th century because it was first found by Peterson, that his famous Peterson graph. That's the graph, cubic graphs that are not 3H curve, smallest cubic graph that are not 3H curve. And since then, people start calling cubic graph that are not 3H curve because snark. So if you use the word snark, then focal theorem is equivalent to say that no snark is planar. And it's even known that the snarks are not double cross. Double cross means this is a planar graph with 2 crosses like this in the boundary. I don't know at the apex. And this is already proved by Robertson, Simmons, Sanders. So motivation is the following. This is so far what's known. So what can we say? Can we do better? Can we push further? That's the main motivation. And we go a little bit different direction. So let me just going to tell you about our main result. So we look at the graph on the surface. And particularly, there are nothing known except for the planar graph, planar graph, which means a sphere. So we should really look at projected plane. That actually be the plane plus cross gap, just one cross gap, meaning that if you embed a graph, all edges are actually cross like pairwise cross like this. And this is smallest genus beyond the sphere. So we should look at this graph. One of the reasons is that the Peterson graph can be embedding projected plane. But what was known so far is Peterson graph is the only snark that can be embedded in the projected plane. And it was already conjectured by 90s by Neil Robertson and Boy and Moher that indeed Peterson graph is the only obstruction. And that was a conjecture, and that's essentially our main result. But in order to say something more, we'd like to talk about a little bit more about the more general thing, because our result is more general. Let's consider the following operation. Let me just go. So again, this is embedding of the projective planar, Peterson graph and the projective planar. We consider the following operation. So this is edge, pick up any edges like here, and then replace inside the edge by some planar cubic graph. That's one operation. The other operation, you look at some vertex here, which is degree 3 here, that corresponds to here, and replace by planar graph. Now, it turns out this is kind of trivial in a sense that once you start from embedding on the projective plane and replaced by that, the edge colorability is essentially the same. In other words, if you can color the edge color the bigger graph, you can color the smaller graph. And vice versa. If you can color the smaller graph, you can color the bigger graph if you do that this way. And so that's why we call trivial obstruction. Then our theorem can be formulated like this. Every cubic graph embedded in the projective planar is 3 edge colorable as long as it's not in the family called Peterson-like. Peterson-like is basically what I said. Starting from Peterson graph, replaced by each edge by the cubic planar graph by the 2H graph, and the 3H graph by like this. And that's actually if and only if, because this family is not 3H colorable. That's a trivial abstraction. So you have to really exclude this family of the graph, but that's the only abstraction. That's what we proved. And using our result, the corollary, the only project planar snap is really Peterson. So that's somehow, what you kind of want to prove, because sometimes the Peterson graph is the only abstraction, and this is one of this kind of a theorem. So that's one kind, our main result restated. And of course, this is stronger than focal theorem because planar cubic graph can be easily embedded in the project plane. So that's what we have proved. And there are some interesting implementation, which is kind of analog of type. So just remind you that let me just use the laser pointer. Title theory says that planar graph is focalable if and only if the bridge's cubic planar graph is 3H graph. We have a similar theorem in the projective planar. So a bridgeless cubic graph embedded in the project plane is 3H graph if and only if its dual is triangulation. If it is triangulation, it's 5 vertical. Unfortunately, we cannot really say 4, but we can show actually 5. That if and only. But this is not really the it's just, I would say it's just accident, but still we have a beautiful result of the type, analog type. At the moment, I really have to tell you something warning. Please don't ask me about computer-free proof. That's not what we are trying to do. In fact, we are going totally opposite. What we did is we actually use the machine power as much as we can to push the method of the focal theorem to the in the general setting. I guess that's probably it's time to do that because machine learning, deep learning, they use a lot of machine power. And at the beginning of this conference, we already saw the song, and that is probably created by the ChatGPT, right? We already know that we have a lot of machine power using that, and we really want to use machine power to push as much as we can. That's what we want to do. So the conceptually speaking, maybe mathematicians really want to see the proof of the focal theorem without using computer. But what we are trying to do is totally opposite. So please don't ask about the computer free proof about something like focal theorem. That's not what we are trying to. We are trying to totally opposite. We use computation power as much as we can. However, we have some interesting way to some verification, computer part verification part. What we do is that we actually provide the pseudocode that gives you the algorithm for our code that you can make sure that our algorithm is correct. And once you understand that our algorithm is correct, you just code what yourself, right? So that's the way to you can sort of reproduce our computation part. And if you're interested in the algorithm, we can actually also give a polynomial time, same as a focal theorem. In the focal theorem, you get like a quadratic algorithm, 3H graph, planar cubic graph, or focal planar graph, and we can get actually the quadratic time algorithm to 3H graph projected planar cubic graph if we can. And indeed, algorithm is just following the proof. All right, so far I've mentioned the result. So far I've mentioned our conceptual thing that we want to do. Now, in order to show our result, in order to show our proof, we have to show a sketch of the proof of the focal theorem because we are trying to extend that. So the next 15 minutes or something like that, I'm going to tell you a sketch of the proof of the Fokker theorem. And in order to prove such a theorem, as you can imagine, you just take a first, take a minimum counterexample, right? In our case, we take a counterexample with now, so n is the number of vertices and m is the number of edges, which we take such a counterexample of n plus m is minimum. So that's why we call minimum counterexample. Now we call such a graph as G to be such a graph. Now, as you can see that, so below n, which is the line, the number of vertices plus number of edges here of G, below it's either 3H curve or Peterson line, because that's what we want to show. And above, it's not 3H curve, or not 3H Peterson line either. So that's what you want to show. And then you just say that this graph doesn't exist. That's what you want to show, right? Then this is basically the same as the Fokker theorem. So what you want to show conceptually is the following. You are going to construct what we call unavoidable set. That means that one of the members appears in the minimum context. So that's called C. And this set C consists of what we call reducible configuration, which means that this doesn't appear in the minimum context. So that would be contradiction because we are trying to construct a set which never appears in the minimum context sample, which never appears in the minimum context sample, but it would appear in the minimum context. That would be the contradiction. And that's what we are trying to do. And these two require what we call two methods. First method is called discharging method. The other called the reducibility check. And let me just try to show you what the reducibility check is. Here is a reducible check. So you start from the minimum context sample. So you want to show that some configuration C will be reducible. And in this case, what you really have to do is the following. Just take up the four pictures here. Take a look at four pictures here. Assume that this configuration appears in the minimum context sample. With this dot edges, real edges. Okay. Now, what I'm going to do is I just delete these edges. Then this degree 2 vertex to be the edges like this, and that's exactly this graph, right? Then we get the smaller graph. Then, assuming that this graph is not the Peterson-like, we get the 3H coloring because we get the smaller graph. Okay, great. Now, delete this part, essentially the center. Then you have like this kind of the links, this kind of the matching edges, half edges like this with a color left. And we plug this one back to here. And if we can extend this coloring into inside, that would be great because we get the 3H coloring. And that's a contradiction. And that's what we want to do. And that's exactly what we want to do. And there's actually one more way to do what we call, that is called Kempeche. So essentially, this is the same as what we discussed, except for this step. So from here to extend the coloring inside, we may do some Kempeche. And that somehow requires sometimes the enumerative combinatorics. Let me show you something. So the Kempeche is the following. It's basically for vertical coloring, it's just like a two-colored path. Like this is purple, green, purple, green, purple, green, purple, green, purple, green, like that. So edge coloring case, this is the same, basically blue, black, blue, black, blue, black, blue, black path like this. And if you have such a Kempe chain, what you can do is that this blue and black can be flipped. So that I can get the black here and the blue here, black, blue, black, blue, black, blue. So blue becomes black, and black becomes blue. Then you get a different coloring, and then you may get a better situation because then you can sort of then sort of you can extend here if you change some color here. So what you really have to do is that, well, I get the coloring of these kind of half edges matching from induction, and I really want to extend this coloring inside the disk, but sometimes you can't. In this case, what I'm allowed to do is what called to do the Kempe chain to flip a color like that. And that's what we call Kempe chain. And the Kempe chain is kind of interesting because that's kind of very close to the enumerated method. So this is exactly the following. Let me write something. So think about, this is exactly the same as the following number. So think about the vertex in the circle. And this is exactly the same as you have a matching, like how many matching you have like the, sorry, this is something like this, which doesn't give you a cross. And that's exactly Catalan number. So you really have to consider all the way of the Catalan, all the number, you have to consider all the matchings, which doesn't give a cross because it's a plane. And that's exactly the Catalan number to consider. So look at this. So this is the number of Kempe chain you have to consider. If you have a 10 edges, you have to consider this many. And projective plate is even more. I'm going to tell you why. But you see, so the link size, this is exactly the number of edges, the half edges here. That can be 16 or something. And at each of the coloring, we have to consider the Kempe chain. So I probably forget to mention, but you see this coloring can be arbitrary. So you have to consider all the coloring because when you apply an induction, you have no way to control the coloring. So coloring can be arbitrary. So you may have to consider all the colorings. But in this case, what's happening is that if you have to consider all the colorings and you have to extend for each of the coloring inside here. So that seems like a lot of cases, right? And in fact, this is exactly picture. The number of colorings we have to consider is this many, like almost like 2 million. And the number of the Kempe chain you have to consider is like this many, or sometimes this many. And this is we have to multiply, which means that you know there's no way to do that by hand. And in projective plate, it's even much more because it may cross like that when the at the cross gaps, and only one cross gaps, but the matching can cross, so it's more than Catalan. So, okay, so again, let me do it again. What you do is that I want to show that this configuration doesn't appear. What I do is basically, okay, delete some edges. Okay, you get a smaller graph. Then this is no longer counterexample. You get a coloring. From this coloring, just delete the inside, and by using a Kempe chain, we extend the inside. But catch here is that you have to consider all the coloring of here. You have to consider all Kempe chain, which is more than Catalan number. That's why you really need a computer check. But once you have the computer check, you can do a lot because even the size, even the size like 14, you can do like a few minutes. Check all the colorings. So, but on the other hand, there's no way but that you can do like by hand. This is almost like already like 200,000, and this is more like 2 million ways to consider. That's no way to do. All right. Oh, by the way, so from this moment, sometimes we consider not only the cubic graph, but actually the triangulation, which is basically the dual graph. Right? So we have a cubic graph, G, and sometimes we consider the triangulation, just probabilities is here, and then just make adjusted if they share edges. And because traditionally speaking, in the focal SEM, it's much easier to consider the triangulation. Now, here's something interesting happening to us. So Robertson, Seaborn, Sanders, Thomas, they have a list of 633 reducible configuration that is necessary. And it turns out almost like 60% of planar reducible configuration are not reducible for us. That's a problem because we really have to find a lot of things by ourselves. But our student, we actually tried hard, and my student really work very hard for like few months, and we made it. Instead of 633 for planar case, we had 5,076. That is a lot, but that's still okay. And so that is like somehow the complication for planar case. So far, Robertson, Seymour, Sanders, Thomas, they got 633 reducible configurations they have to consider. But in our case, we have to consider 5,076. Okay, but still, we made it. It's a finite number. So that's about the reducible configuration. So reducible configuration is basically saying that the configuration doesn't appear in minimal context. But if you have such a set, we have to show that one of the 5,076 in our case. In the planar case, one of the 633 must appear in the minimum context sum. For that, we will do what we call discharging method. For that, we need like some rules. In our case, it's 169 rules. And for Robertson et al., that's 32 rules. Oh, by the way, the Apple and Hacken, that's like more than 300 rules. I have no idea how they actually control. But anyway, so let me present what the discharging method is. So discharging method is going like this. So initially for each vertex of degree D, we assign the charge 10 times 6 minus degree. For example, this guy the degree 5, so this guy gets 10. So this guy is degree 7, so they get like minus 10. Because if you put a plug in that 7, then that will be minus 10. And by Euler formula in the dual, so we are considering the dual graph here. That's why it's a triangulation. If you sum up everything, by Euler formula, we know that the sum will be positive. Not only the planar case, but also the projective planar case. This means there is some vertex which is positive somewhere here. For the positive vertex, we want to find that there is actually reducible configuration nearby here. But in order to do that, we have to show that not only the positive, we have some called rule. Here is the discharge. Discharging is quite easy. It's all local. So you have a rule according to the edges. So each edges, you have a rule. And so you have a rule, and each edges, you have to apply the rule. And according to rule, you send some charge. For example, this rule exists. So this rule exists. So this vertex sends some charge here, and this vertex sends some charge here. This vertex sends some charge because of that. So each of the edges you apply each of the rule. It may not apply anything, but you just apply rule to move the charge if necessary. So the rule is just sending a charge from each vertex to send something, and in the end, again, because this is a sum is the same, so what you do is that because this is positive, you have a positive vertex somewhere here. For example, this is a positive guy. Then the positive guys has a property that there is a reducible configuration within the surname. In this case, you have like a reducible configuration here. That's essentially the proof of the focal theorem. By the way, so this discharging rule is not really that hard in the sense that you can do that by hand if degree is 6 and the degree at least 12. And 7 to 11, you have to do the computer check. But this, I think you can actually write down if you want. This like if you're allowed to write 50 pages or something like that, then you can check, you can write down everything. But still, it's much better to use the computers from my perspective because computer never make a mistake. All right, so this is what happened. We obtained the unavoidable set that consists of 576 reducible configuration, meaning that we have a set of 5076 reducible configuration that must appear in the minimum count example. And to show that that must appear in the minimum count example, we apply the discharging method with 169 rules, and it turns out this is enough. Okay, then that gives a number. That means that there's no minimum count example contradiction. And the focal theorem case, and this number is much low, like 32, and we have said 169. And the 633 reducible configuration is replaced by 5076. Good. Okay, so now I finished the first half of my talk. And the rest of the maybe 15 minutes, just say something about the difficulty. Well, are we done? It seems to say that the minimal counter example doesn't exist. And in fact, this is exactly the focus, what the proof of the focus I'm doing. But in our case, there are few difficulties. And in fact, two most difficult parts. First thing is really actually the annoying part. So reducible configuration is that once you make a reduction, you have to get the 3H coloring. That's a condition by induction. And in the focal theorem case, that's always the case. I'm going to tell you why. So induction does work. But in our case, may not be here because, well, when you make a prediction, are you sure that you never end up with Petersen-like? If we end up with a Petersen-like, we never get the 3H coloring. So that's a problem because we can't really extend the coloring. So that's one thing we have to make it clear. The second thing is that planar and the projective plane are totally different. There are some difficulties for projective. Can you make it? So these two are real difficulties over the focal theorem. So let me just look at the first one. That actually makes a difference between the focal theorem case and our case. Before that, I'm going to tell you why this is a problem. If you look at reducible configuration, the planar case, they actually have to delete only 4 edges or four edges to contract. In our case, it could be at 5 or 8 edges to contract or delete to make a reduction. And that's going to be the problem. And in fact, we have 5 edges to delete. It's like more like this many red parts. That's a dangerous zone. I'm going to tell you why. To begin with, as I said that two difficulties I presented are not problem in focal theorem. Why? In order to show that, we have to make sure that these two are true. So what we are trying to do is that sometimes when make a deduction, you have to delete some edges. It's like here, you may delete these red edges, and then you make degree 2 vertices to be the edge. That's what we're going to do to make a reduction. Then, are you sure this is a planar or cubic? And this is actually good, easy to show. And another thing is, are you sure that this is a bridgeless? Keep in mind, for the planar graph, what you have to do is every bridgeless cubic planar graph is 3H curve. So you have to make sure that it must be bridgeless. So they, for the focal theorem, they have to make sure that this has to be bridgeless. And in fact, it is bridgeless because minimal count example is cyclically 5H corrected. You can't really get such a separation. So for them, it's free. Great. But in our case, there are more to be said. We have one more family called Peterson-like. Firstly, is it projective planar? Is it still embedded or cubic? Well, that's actually good. Not so much of. Is it bridgeless? That's we have to check a little bit more, but it's not that hard. The hardest one is actually the following. Is it actually Peterson-like? Well, that's a non-trivial at all. That's what we have stacked for a while. Essentially, the problem is, so that we need to make sure, right? So Peterson, if we end up with Peterson-like, that's a problem because we can't really color it. The problem is the following. Look at this graph. So this is actually the Peterson, sorry, this is embedded in the projected plane, where this edge is actually connected here, this edge is connected here, and this edge is connected here. And assume that we have to delete these bow edges. So far, this graph is not Peterson. But once we delete these bow edges, what happens is, okay, so this way. And these 2 degree 2 vertices, these 2 degree 2 vertices are gone like that. Then this is a problem because you have like a 3H curve like this. So you may have this situation to going backward, so opposite way. But this is exactly what happened. So once I'm going to crash down to 1, that's going to the Peterson graph. That's a problem because we make a reduction, but we end up with a Peterson-like. Oh my God, we can't really apply the induction. And that is actually the big problem for us. So the problem is that firstly, the minimum context doesn't have such a 2 or 3H cut. But on the other hand, if we delete some edges to make a reduction, we have to delete some edges, like the previous case. Then we may get the 2-3H cut. And after do that, you make a 2H cut, 3H cut to crash into one vertex, it may end up with a Peterson graph. Oh my God. And that actually happened with this red part of it to delete. Oh, by the way, so this 5776 is the number that I mentioned for reducible configuration. And these are the number of edges to delete. So that's a big problem. So to get rid of this problem, we can't really completely get rid of this problem, but it turns out there are 2 weapons we get. One weapon, what we call small disk cut, which means the following. So again, this example, in the original graph, what happens is that you see that this is a 6H cut going like this. And after you delete these black edges, you end up with some Peterson-like. Therefore, if you have a small edge cut, contractive edge cut like this, that gives something for us. And that's exactly the motivation to what we do. So suppose such a cut of size 6 or 7 happen, that banded disk. Then what happens is there is actually a reducible configuration inside, strictly inside the disk, meaning that inside here, or the disk bounded by is basically very small. In the dual graph, it looks like this. So it means that if we see like this kind of 6H cut, we better look at the inside. And we better look at the inside to then find reducible configuration. And that's what this claim. We look at the smaller side, better look at the smaller side, which is easier because inside make a reduction and outside basically stays same. So it's less dangerous. Otherwise, we can safely reduction. That's great. So that's one weapon. The other weapon is what's called projective island. Again, we have the similar situation. After you delete, look at the disk 6 edge cut and delete this and crash it into one vertex, you get a Petersen graph. So we should look at the counter operation. This is the following. So this is a Petersen graph. And look at one vertex and blow up this way. But you may add edges between in this cycle. And it turns out this configuration is outside is reducible up to the size 178. And that helps a lot. So that's one weapon. Okay. And it turns out these two weapons get rid of a lot of guys. So we have a dangerous like this kind of danger. So something like 1400 guys are really dangerous because we have to make sure that after make a reduction, we don't end up with Petersen like. And it turns out the two weapons get rid of almost every single possible except for five. And these five we checked by hand. Luckily, everything seems good. So that's the story. The second difficulty is that this is a projective planar. It's not planar, so we have a difficulty. So imagine the following situation. I have planar embedding here. If this is induced, then this is reducible. But it may be the case that blue and yellow are adjacent because of the non-planar embedding, actually projective planar embedding. And this case, it's not good because the reducible configuration is wrapped up, which is not really reducible. So we have to say something. It turns out that this can be formulated by what is called representativity, meaning that if these guys are adjacent, you have a curve like that that's hitting only small number of edges. And if this is small, that's a problem. And if there are no such a small curve here, as I said, it's good. We can always find a reducible configuration, which is still reducible, not wrapped up. But if this is small, then we can do something else. And what something else is that if representativity is small, then we get like something like this kind of subdivision. And it turns out this kind of subdivision is reducible. That's what we do. There are actually a few thousand of them. We check all of them are reducible, luckily. And that's actually very similar to the argument in the double cross paper by Edwards, Seymour, and Robin Thomas. All right, so what is it? We get like 169 rules that's discharging. We get a 5076 reducible configuration, and these are all good. And this must appear in the minimum context of contradiction. And there's several difficulty, but we made it. We made it. So in the end, what we get is this theorem stated. So if BTS project planar cubic graph are embedded in if the bridgeless cubic graph is embedded in projected planar, the either it is sledge graph or it must be Petersen-like. And if you stick to snark, only projected planar snark is a Petersen graph. So that we have. So that's strongest statement. So let me conclude. We proved that the only projective planar snark is Petersen. That a generated system with a focal theorem, and you need a lot. We do need a lot of computation power. Now we work on something else. In fact, because we know that we still have enough computation power, and we feel that we should push further. And obvious target is actually torus. It was actually the conjecture by Grunberg, 1968, and the Kleinbottom. And there's another thing we are trying to do. That's what's called subcubic graph. Subcubic graph is it's not cubic, but max degree is 3. Max degree is 3. So there are vertices degree 2 there. What we are trying to do is subcubic case. This is subcubic planar graph. Unfortunately, I forgot the planar. But subcubic planar graph, that is really Grotje's conjecture. And in this, the four-flow conjecture is really the status four-flow conjecture. In order to prove that status four-flow conjecture, you really need to get rid of subcubic case indeed. So the only thing I like to talk about a little bit is the torus case. We actually did a lot. We already did this almost like 8,000 reducible configuration, the 201 rules, and many, many more. And we actually get something very similar to the projective plane. And I thought we are done, but not really. So we have a challenge by Euler from the 17th century. What he asked us is the following. Are you really sure that there's always a vertex of a positive charge? Keep in mind, what we show is by using the discharging method, there is a positive vertex here, and nearby the positive vertex, you can find a reducible configuration. That is the main theorem that we did. The Euler asked us, are you sure that there's a positive guide? Well, as I said here, not really. This is really because the torus case is really, this could be 0. This could be 0. So that means that it's possible that every vertex gets 0 charge. And what do you do? And this is unbelievably hard. And that's what we couldn't get rid of at the moment. But we hope that this can be done soon. So that is a torus case. And the Kleinbottom case is probably similar. That's what I expect. So we actually would do a torus case and together with the Kleinbottom case, and we hope that it will be done soon. But on the other hand, you could ask that, can we go further for the higher surface? And the answer is no, because for the Koho, he has some counterexample, a lot more counterexample when the genus is like 5, something like that. So we can't really go further. But at least we want to finish torus and Kleinbottom. And it's probably much more than the projective plane and much, much more than the focal theorem, but still, computation power can be probably bring us to this level. Again, the subcubic planar case, that's what's called Grotje's conjecture from the 1960s, and it's really the main obstacle to the status four-flow conjecture. So I think, but still, we still have hope that our computation power can help us to do something. But we see, sorry, this has to be true. This needs a lot more work. I kind of believe that this can be doable if we work harder, but the second subcubic planar case seems like much more work needed. And of course, to attack that status four-flow conjecture, we do need more. All right, so I guess it's almost like time's up. Finally, I like to talk about most important theorems, and every cat's focal because cats are homomorphic to the sphere, so by the focal theorem, you should be able to focal. Thank you. Thank you very much.